A rectangular concrete beam 100 mm wide by 250 mm deep spanning over 8 meter is pre-stressed by a straight cable carrying an effective pre-stressing force of 250 kN located at an eccentricity of 40 mm. The beam supports a live load of 1.2 kN per meter. Calculate the resultant stress distribution for the center of span cross section of the beam assuming the density of concrete as 24 kN per meter cube. Also, find the magnitude of pre-stressing force with an eccentricity of 40 mm, which can balance the stress due to dead end live loads at the soffit of the central span section. So, in the pre-stressed concrete subject, most of the time, the problem statement will be highlighted. From the problem statement, it is needed to understand it clearly and then to draw the sketch. So for the given data, let us try to draft the sketch. So here, let us understand that the beam dimension is 100 mm by 250 mm in cross section. This is the width of the beam. This is the depth of the beam. The dimension of the beam is given as 100 mm by 250 mm. So this is width 100 mm and depth is 250 mm. And this is cross section. So let us understand the longitudinal section. It is having the length of 8 meter and the beam carries a live load of 1.2 kilonewton per meter and it is pre-stressed by a cable which is having the pre-stressing force of 250 kilonewton which is located at an eccentricity of 240 mm, and we have to note it importantly that the eccentricity always is to be drawn with respect to the centroidal axis. So this represents the centroidal axis or the neutral axis. Eccentricity has to be drawn always with respect to the neutral axis, and the beam dimension overall is given as 100 by 250 mm, and let us draw that accordingly. And this is the depth of the beam, and this is the two-dimensional view or the longitudinal view of the beam, and it carries an uniformly distributed load of 1.2 kilonewton per meter, which is given in the problem statement, and the span is 8 meter, and here the pre-stressing force P of 250 kilonewton is applied. And from the given data, we need to compute several basic requirements like cross-sectional area. The cross-sectional area is computed as, since it is a rectangular cross-section, the cross-sectional area of the rectangle section is 100 by 250, and that is how we have got 25 into 10 to the power 3 mm square. And next, eccentricity is given in the data. Self height of the beam, let us calculate. Here I have considered G as the notation, that is WG as the notation for the self height of the beam, whereas Q represents here for the live load. WQ represents the live load, WG represents the dead load. The dead load can be calculated as area into density. Area can be calculated as 0.1 into 0.25. The unit conversions will be made accordingly. Live load given is 1.2 kilonewton per meter. And section modulus, that is Z is equal to BD square by 6. This is the formula for the rectangular cross section. It depends upon the cross section of the concrete member and it varies. For the rectangle, it is considered as BD square by 6 and it is computed accordingly. And next, dead load of the moment, dead load for the dead load bending moment at the central span section. As all of us know, the dead load bending moment expression for the simply supported beam carrying UDL throughout the length is given by, this is the bending moment profile, and the bending moment at the central span, this value is given by WL square by 8, and it is same for both dead load as well as live load, and it is considered here for the central span section, and it is computed as 0.6 into 8 square by 8 and it is obtained as 4.8 MQ. Similarly, it is computed as 14.4 kilonewton. And coming to the first part of the problem, that is it is required for us to calculate the direct stress due to the pre-stress, and it is given by the expression P by A. That P by A is nothing but the general stress expression, sigma is equal to P by A, and accordingly it can be computed. And bending stress due to pre-stress is given by plus or minus PE by Z. After substituting all the values, it is obtained as 9.61, and bending self-weight stress is calculated as plus or minus mg by Z. 4.8 into 10 power 6 divided by substitution of Z value, it gives 4.615, and similarly live load stress is calculated as plus or minus mq by Z, and it is obtained as 9.23 Newton per mm square, and the resultant stress is given as F superior with respect to the topmost fiber. It is given as P by A minus PE by ZT plus mg by ZT plus mq by ZT, and whereas F inferior, that is stress at the bottommost fiber, is given as P by A plus PE by ZB minus MQ mg by ZB minus MQ by ZB. See, this ZT and ZB is a generalized expression. As I've told you, it is a rectangular problem, so we have a common Z value. However, this value varies for an I sections or an unsymmetrical sections or the flanged sections accordingly. After substituting, finally we get the stress at the topmost fiber as 14 Newton per mm square and the bottom as 5.7 Newton per mm square. And now it is required to plot the stress distribution. So how to draw that? And earlier we have understood that the sign convention for the compression, it is always positive, and tension, it is negative. And from the fundamentals of concept of pre-stressing, we are very much aware where are we going to expect tension and where the compression is expected. Since the bending stress due to the direct stress, we have obtained it as plus 10, we have considered that compression, it is always taken as positive, and let us draw a reference line. So here at the right top corner I am taking one reference line. Since it is positive, whatever the values we get positive, we are going to draw it towards the right of the reference section, and that is how at the top also we have got 10, bottom also we have got 10, and that is how we have plotted sigma is equal to P by A, that is it is entirely compression. The fundamental concept of pre-stressing is that we are going to impart the pre-compression to the concrete member, and that is why the direct stress due to pre-stressing is always positive. And second one, the second sketch, what we can able to notice here I have drawn one vertical line. Depending upon the F superior and F inferior equation, we know that for F superior, that is with respect to the top fiber, it is negative. So it can be noticed in the F superior expression. So we have drawn it towards the left of the reference line, and when it comes to the F inferior, and it can be noticed here plus PE by ZB, and that is how it is being drawn. And similarly, if we come to the third sketch, and here this one, wherever I am highlighting, it is minus, therefore it is drawn to the left. And similarly here the last value MQ by ZB, that is also negative, therefore it is being drawn to the left here. And next, if we consider the compression, that is F superior, here at the top it has to be drawn to the right side, because F superior expression and the fundamental concept of pre-stressing, it is positive. And coming to this sketch, this is also positive due to the live load, and then directly connecting. And finally, the resultant stress what we have computed after taking everything into the calculation, I have drawn one reference line. The final value we have obtained it as plus positive plus 14, therefore it is drawn to the right side. And here F inferior also it is drawn, it is to the bottom. And this is how this stress distribution is obtained. And see, it can be noted here. F superior, here it is plus 10, therefore it is 10, minus 9.6, therefore here minus, it is taken to the left, plus 4.65, therefore it is drawn to the right of the reference section, plus 9.23, it is drawn to the right of the reference section. And accordingly F inferior also it is being drawn here. And next, the second part of the problem is that you have to find out the magnitude of the pre-stressing force with an eccentricity of 40 mm, which can balance the stress due to dead and live load at the soffit of the central span section, which means balancing is nothing but we are trying to keep the system in equilibrium. Equilibrium means balancing, that is we are trying to equate the soffit of the central span section stress equal to 0, which means F inferior expression is equated into 0. That is soffit is nothing but the inferior. F inferior, it has to be balanced, and then that is how we are equating. So that is why we are taken the F inferior equation equate into 0, taking this P common outside and sorting out. Finally, we get the value of P as 176.